T flip-flop and JK flip-flop using behavioral modeling, and we will discuss the test bench, how to write the test bench for this JK flip-flop and T flip-flop. So first we will start with our, wait a minute. So we'll start with our JK flip-flop. So I've created a file for JK flip-flop. So within a, wait a minute. So I'll create a module called JK underscore flip-flop underscore behavioral modeling, and the inputs are my JK, sorry, clock, reset, J and K, and my outputs are Q comma Q bar. So these are my inputs and outputs of my JK flip-flop, and within always block passage of clock, this is a positive edge flip-flop. Begin, so begin, I'll write since output is wire type, so we cannot use it in always block, so I will declare some register called q underscore reg and q bar underscore reg. So these are my two registers which I can use in always block. So q underscore reg will be equal to, see, I am using non-blocking assignments. Q underscore reg equal to sorry, so if reset, q underscore reg will be equal to 0 and q bar underscore reg will be equal to 1. Else if j is equal to 0 and k is equal to 0, then q underscore reg will be equal to q underscore reg. This is a wait a minute. So we should use begin and if we are using multiple statements inside an if. So we should use begin and if we are using multiple statements. If only one statement, then there is no need to use begin and. So begin comma end. So when j is equal to 0 and k is equal to 0, it is like a hold condition. It will hold the previous values, and q bar underscore reg will be equal to q bar underscore reg. See here, I am using the non-blocking assignments here. Since I want the output of the flip-flop simultaneously, I want the two outputs to be driven simultaneously. If I use the blocking statements, then then after executing of first statement, the second statement will be executed. That is, second statement is waiting for first statement to get executed if I use blocking statements. Whereas if I use non-blocking statements, it will run parallelly. So I want the outputs to get parallelly. So the outputs of the flip-flop should be driven parallelly. So I'm using non-blocking statements. So that is the reason why I am using non-blocking statements. And k is equal to 1. This is a reset condition. Then begin, q underscore reg will be equal to 0 and q bar underscore reg will be equal to 1. Ending this, and else if j is equal to 1 and k is equal to 0, then begin this, q underscore reg will be equal to 1 and q bar underscore reg will be equal to 0. And the last condition, when else if j is equal to 1 and k is equal to 1, this is a toggle condition. So if j is equal to 1 and k is equal to 1, then it is a toggle condition, that is begin q underscore reg will be equal to q underscore not of q underscore reg, and q bar underscore reg will be equal to not of q bar underscore reg, ending this and ending the always block. So this is a Verilog code for behavioral. So this is a behavioral modeling of JK flip flop, and I will assign finally q is equal to q underscore reg and assign, sorry, so I cannot use non-blocking statements with assign keyword. So q bar is equal to q bar underscore reg and ending the module. So this is the Verilog code for JK flip flop. Is it clear for everyone? Is this coding clear? So let me write the test bench for this also. JK underscore TB. Let me declare the inputs as red and outputs as wire q comma q bar. And my design name is jk underscore ff underscore beh. So jk underscore ff underscore beh. This is my instantiation. First step is to instantiate our design. This is the module name and this is the instance name. So clock, I'm doing positional instantiation. So according to the position, so in the here at the first position we have clock reset j comma k. So I'm instantiating by position. So clock reset j, k, q and q bar. Now the next step is to generate the clock. So for generating the clock I will use always hash. Now we'll generate 20 time period clock, not of clock. So that so the time period of this clock is 20 nanoseconds, and I will initialize my clock. So before this only I will initialize my clock. No problem, after this also we can initialize, but before this statement I will initialize my clock reset jk is equal to 0. So initialization is must, because if we have not initialized, then the default value of reg will be equal to unknown, then we will get the unknown only. So that's why I'm initializing my inputs, and within an initial beginning block I'm going to drive the inputs. So at neg edge of clock I'm going to drive the input since it is a positive edge design. So at neg edge of clock reset is equal to 1, and at neg edge of clock reset is equal to 0, and at neg edge of clock my j is equal to 0 and k is equal to 0. This is my first input, and at neg edge of clock j is equal to 1 and k is equal to 1, and at neg edge of clock again I am going to give j is equal to 0 and k is equal to 1, and at neg edge of clock I'm giving j is equal to 1 and k is equal to 0. So these are my some of the input combinations to my design. So is this test bench clear? So is it clear how we write a test bench for a flip flop? Is it clear, right?
Yes, bro.
Yeah. So these are the steps to be followed for sequential circuits. So we will also discuss how to write the test bench for combinational circuits. So for any sequential circuits, uh, in the case of flip-flops, this is the, wait a minute. This is a standard procedure. First, instantiate the design and initialize the inputs and generate a clock. And if the design is working on the positive edge of the clock, then drive the inputs at negative edge of the clock. So this is how we write a test bench for a sequential circuit. So let me save this and run this. So before running this, make sure that both in simulation and design, the file should be made as top. So right click on it and click on set as top. And in the design also, it should be top. Set as, wait a minute, it will take some time. So initially, I'm driving reset at negative edge of the clock. So the outputs will be equal to 0 at positive edge of the clock. The output is getting 0 at positive edge of the clock. That is q is equal to 0 and q bar is equal to 1. And I'm driving another input, that is j is equal to 0 and k is equal to 0 at negative edge of the clock here. And I'm getting at positive edge of the clock, it is a hold condition. When j is equal to 0 and k is equal to 0, output will be same as the previous outputs. And again, I'm driving j is equal to 1 and k is equal to 1 at negative edge of the clock. So the output should get toggled. So it is happening at positive edge of the clock. Here we can see q is becoming from 0 to 1 and q bar is getting changed from 1 to 0. Again, I am changing the input of input j and k at negative edge of the clock. Uh, j to 0 from 1 and k I am keeping it as 1. That is j is equal to 0 and k is equal to 1. That is reset condition. So q is getting 0 at positive edge of the clock. My output is getting at positive edge of the clock and q bar is equal to 1. And again, j is equal to 1 and k is equal to 0, I am giving at negative edge of the clock. So at positive edge of the clock, I will get the output, that is q is equal to 1 and q bar is equal to 0. So this is how we write the design and test bench for flip-flops. This is the code for JK flip-flop. Is it clear? If you are having any,
Bro,
yeah.
bro, uh, why we get it here? Not don't care.
Initial values of registers are don't care. So here we can see.
Okay.
So initially we don't know the values. So it will be not equal to 0 or not equal to 1 before applying any reset condition. The output is in don't care state. We don't
Okay.
know whether the output is 0 or 1. So that's why we are
Okay.
applying reset condition to make the
Oh,
output to a known state, here to 0.
okay.
Okay.
Oh,
Yeah.
okay, bro.
Yeah. So this is the code for JK flip flop. And now let's code for T flip flop. And here the T flip flop will be, let's code the T flip flop as a uh, active low T flip flop. So it will get activated at neg edge of the clock. So we will see how to write the code for a neg edge flip flop. So inputs are my clock and reset, same, and input is T and outputs are q comma q bar. And let me declare two registers, q underscore red and q bar underscore red. So these are my two registers, and within an always at the rate, instead of writing positive edge we will write negative edge of the clock, neg edge of clock. Simple. This is a change. For positive edge working flip-flops we will write pos edge. For negative edge flip-flops we will write neg edge. So this is the difference between those two. So if reset And till now we have written the code for synchronous flip-flops, synchronous reset flip-flops. This is a synchronous reset. So synchronous reset meaning is the reset, when we apply the reset, the output will get affected at the positive edge of the clock. So that is, the reset is working according to the positive edge or negative edge of the clock. That is, the reset is synchronous to the clock. That means if we apply the reset, then the output will not get immediately changed. It will change at the positive edge or negative edge of the clock. That is the synchronous reset. But if we use an asynchronous reset, then the when we apply the reset, the output will change immediately. It will not wait for the positive edge or negative edge of the clock. Is it clear? That is the difference between the synchronous and asynchronous reset. If we are using this if reset inside an always block, then it is a synchronous reset. So remember this. This is also a very important question. So they will give a snippet and ask if the reset is synchronous reset or asynchronous reset. So according to the reset, where we are using, inside the always block or within the, wait, I will show it. So remember this. This is a synchronous reset. So I will show the snippet for asynchronous reset also. So always at the rate neg edge of the clock or reset. So if you see the snippet like this, so this is an asynchronous reset. So if there is any change in the clock, or if there is any change in the reset, or if we apply any reset signal, then the output should be then the always block should be triggered. Whereas in case of synchronous reset, if there is only change in the clock, wait a minute, I will show this. Yeah. So in case of synchronous reset, if there is change, if there is change in clock only, the always block will be triggered. If there is a change in reset without applying a clock, the always block will not be triggered. But here in this case, in case of asynchronous reset, if there is any change in reset, irrespective of this clock signal, irrespective of positive edge or negative edge, if there is any change in the reset signal, then the always block will be triggered and the logic will be executed. Is this clear about synchronous and asynchronous reset? So if reset, then begin q underscore reg will be equal to 0. So this is a very important point. Many questions will be asked from this also. Q bar underscore reg will be equal to 0. If you are having any doubt, you can ask me. If t is equal to 0, sorry, this else if t is equal to 0, then begin q underscore reg will be equal to not of q underscore reg. Basically the output will toggle. If, sorry, t is equal to 0, the output will remain as it is, q bar q underscore reg, and q bar underscore reg will be equal to not of q bar underscore reg, ending this. And else if t is equal to 1, then begin q underscore reg will be equal to not of q underscore reg. The output will toggle if t is equal to 1, and q bar underscore reg will be equal to not of q bar underscore reg. So basically if t is equal to 1, then output will get toggled, and that's all. Ending this and ending the module. So let me show the asynchronous behavior of asynchronous reset with the help of waveform. So let me create a TB. So my input should be reg type, reg clock reset T, and my outputs are wire. q comma q bar, and I should instantiate my design. So that is t underscore ff underscore beh. Design name is t underscore ff underscore beh dut clock reset t q q bar. So if you are a beginner in the Verilog coding, then don't prefer positional instantiation. Do prefer instantiation by name. So positional instantiation is not preferred initially. So initial begin, I will initialize my inputs clock reset and t to equal to 0. Ending this, and within an initial, sorry, next step is to generate a clock. Always #10 clock is equal to not of clock. I've generated a 20 nanoseconds clock, and now within an initial begin block I will give reset is equal to 1, and after 10 nanoseconds I will give reset, sorry, is equal to 0. See here in the TB, in the previous TB, I am driving the reset signal according to the clock, that is at the rate neg edge of clock I am driving the reset signal. But here in my design I am using a asynchronous reset, so I don't need to drive my reset signal according to the clock. I can give my reset signal as it is. So without needing any clock, I can drive my reset signal. So again after 10 nanoseconds I am driving the input. So input is synchronous to clock, so I should drive my input. So at pause edge of clock I am driving my input t is equal to 1, and at another pause edge of clock I am driving my input to 0. So here I am using my positive edge of the clock since my design is working on negative edge of the clock. So I should provide my inputs to the design at positive edge of the clock. So this is the difference between the design working with positive edge of the clock and negative edge of the clock. If the design is working with positive edge of the clock, then I should drive my inputs at negative edge of the clock. And if my design is working on negative edge of the clock, then I should drive the inputs to my design at positive edge of the clock. That's why I'm giving my inputs at positive edge of the clock. So is it clear? Okay, I haven't given it. So within an assign statement I should drive my outputs also. I forgotten it. So assign q is equal to q underscore red, and assign q bar is equal to q bar underscore red. So let me relaunch the simulation. So see here I am giving the reset input asynchronous to clock. So I'm giving reset signal, so my output is getting 0, and I'm driving my t input at positive edge of the clock, and my output is getting toggled at negative edge of the clock. Since the design is working at negative edge of the clock, I'm getting q is equal to 1 and q bar is equal to 0. And observe the difference in previous design. Until I get the positive edge of the clock, my output is getting not getting equal to 0, and it is in the unknown state only. But here since the reset is asynchronous to clock, that is it is not depending on the clock. Whenever I apply the reset signal, my always block is getting triggered and my output is getting 0 initially only. So if you observe in the previous design, uh, until we get the positive edge of the clock, even though we have applied our reset signal, but until we are getting the positive edge of the clock, my output is in the unknown state only. It is getting 0 after reaching the positive edge of the clock. But here my reset signal is asynchronous to clock, so it is not waiting for the clock to come. So the always block here, the always block is not waiting for the clock. If there is an if the reset signal is applied, then this always block is triggered and my outputs are getting equal to 0 and 1. Here you can observe, so initially only after immediately applying the reset signal, my outputs are getting changed. So in the previous design, the always block is waiting for positive edge of the clock. So let me change the argument in the always block so that it will be more clear. So I will remove this reset here in the argument, and let's see the output. I should change the TB also. I'll drive this to positive edge of the clock. Now let's see. See, so after applying the reset, we are not getting our outputs to 0. So the always block is waiting for the negate of clock. So as soon as we get the negate of the clock, always block will be activated and output will be equal to 0 and 1. So if we apply reset in this argument or reset, now let's see what happening here. So initially uh, here we are applying the reset, but our output is getting 0 at this net gauge. But here, as soon as we are applying the reset condition, the always block is not waiting for the negative edge of the clock. It is making output to 0 and Q bar to 1. So this is the synchronous and asynchronous reset design, working of synchronous and asynchronous reset.